Now, because there will be situations where you need to evaluate or solve a log to a base other than 10 or e, which is also involves a number that we're not familiar with. Like, remember I said before, we wouldn't be asked to find a log of 25 to base 4, for example. Well, because we don't know what to raise 4 to get 25. Well, in fact, you could be asked to do that, and you can actually evaluate that situation, although we don't have base 4 on our calculator. We can use this other rule in order to change the base, because what this change of base rule allows us to do is to change to our preferred base. Change a base expression into our preferred base. So let's have a look at it. It says the log of x to base a, so I was saying log 25, for example, to base 4, could be written as log, and this b, base b, is our preferred base, our choice. Now, if I'm considering using my calculator, I'm going to make that 10. I'm going to make my new base here be 10. On the calculator, that's simply using the log button. So I'd have log 25, because it's saying log of the x, log of the number, divided by same base, log to base 10, in this case, to the 4. So this then, I would be able to go to the calculator and evaluate log of 25 divided by log of 4. So, advantages of the change of base is I get to choose the base that I convert this log expression into. I could have similarly chosen base e, and remember the abbreviation for log to base e is ln. So ln 25 divided by ln 4 will give exactly the same result as log to base 10 of 25, the log to base 10 of 4, and it will give the exact expression, well, it will give the expression answer, evaluate log of 25 to base 4. So, when might you use this? You might use it when solving an equation. You might use it in evaluating. And yeah, there's another example here. We actually know the answer to this, log of 8 to base 2. We do know the answer. The answer is actually 3. We know that. So, if you take your calculator, apply the change of base rule, which is log to base 10 of 8 divided by log to base 10 of 2, and remember it's just written as log 8 and log 2, then actually do that on your calculator. So here we go, log 8, oh, whoops, I'll just clear that, get my fraction up, go again, log 8, close bracket, come down, log 2 equal, what did I not do right there? Actually, all I think I left out in the previous one was this final bracket. Now, I found out before that if you don't, sometimes it's fine, it seems to understand when it doesn't have that final bracket in, but it doesn't when you involve an expression in a fraction. So, yeah, just be aware of that. So obviously, yeah, it worked, and we can see there that change of base, my choice was log to base 10. Let me just clear that and confirm for you that we could have used ln of 8, and this time I'll make sure I close the bracket, over, so I'm using log to base e facility this time, of 2, close the bracket, equals, and you get 3. So then you can see that it doesn't matter whether it was to base 10 or to base e, that you'll get the same answer. So it really is your choice. Yes, we knew it was 3. We could have used base e, which I've shown you, and you know the answer is 3. How does that help when solving an equation? If you're and you use logs to solve an equation where x is in the power, so please remember that. We know that if we took the log of 15 to base 3, then we're looking for the power to which raise 3 to. So the log of 15 to base 3. Now, I'll need the change of base rule. So log 15 divided by log 3. Let me see if I can change some of this. Delete and make that 3. And go up and back and delete that and make that 15. Now press equals, and 2.46, so I'll round that to 1 dp, 2.5. Oh, I've got 2.46 there. So this first example here is straight out evaluate, log 5.9 to base 4. I'll use a change of base, so it's log 5.9 divided by log 4. 5.9, close the bracket, and then 4, make sure I close the bracket, equals 1.28. Example 2, solve correct. Solve now, so that was evaluate. Solve means we're finding the value of the pronumeral. Correct to 2 decimal places. So I'm looking for that whole power. So if I take the log of 11, the log of this number, to base 4, that should give me x plus 1. I'll go to my calculator to evaluate the log of 11 over the log of 4, and I know that's equal to x plus 1. So x will be whatever log 11 over log 4 subtract 1 actually is. And there you can see log 11 divided by log 4 subtract 1 is this 0.729. Let's write that as 0.73. And the next example is solve again, so find the value of the pronumeral. Now e is not a pronumeral, e is this number, it's 2.718 blah blah blah. So we're not finding e, we're finding the k, we're finding the power. So to find the power, we can take the log to base e of 200, and that gives us k. It says to 1 dp, let me move that over. We simply want the log to base e of 200. Close the bracket. And what was that? To 1 dp, that's 5.3. So k is equal to 5.3. Another solve. So this time we're solving for t, we're solving for the power. I think here, I don't like this m0 and m0, and I don't know what it is. I'm going to just divide both sides by m0 to start with. It's a solving technique, provided m0's not 0. So it's e to the 0.023t. So if I take the log of 3 to base e, to this base, then I'll get 0.023 times t. So we know that to get the t by itself, I want this log number, and I would eventually divide it by 0.023. So you can see the calculation there, log of 3 to base e, which is ln3, divided by 0.023. It's saying to 2 sig figs. This to 2 sig figs cuts off at the decimal point. Cutting off a 7 will round that 7 up to a 48. So t is equal to 48. And then finally, two general situations to learn off by heart are, if you've got the log of a number to its same base, to a power, then it's equal to that power. You can see that very easily by using, I think it was law 3, where I can take the x to the front of log of to base a of a, and that would be equal to x times, and what do I raise a to get a? I raise it to 1, so and x times 1 is x. So yes, of course, this is equal to x. And then finally, this situation, in general terms, if you've got a number raised to a log, so the power is a log, to that same base as the base here, now that's important, those two are the same base, then you know that that left-hand side simplified is simply x, is simply that number. So if we had m to the log base 3, no, m, let's do it in numbers. If you have 3 raised to log to base 3 of 10, then you know your answer is 10. These two bases are the same, and you're taking the log of a number, then the solution, or the evaluating that whole thing, is 10. That's common, that comes up often, and so it's important to realise that. The proof of it is not important. It just says to show it. Then a little technique is, and you'd have to know to do this, that let that index actually be called y. Let the index be y. So your left-hand side becomes a to the y. So the left-hand side is this a to the y. But if we look at what we've set up here, from 1, we know that this base a, or the power, y is the power to which a must be raised in order to give x. So from 1, I can write x, this number, is this power raised to y. But now I've got two things equaling a to the y. I've got two things. They're both a to the y. X and the left-hand side. So if I go back and state that the left-hand side is this thing, a log to the power log x base a, and the other thing that I've got a to the y being is x, is the first statement, therefore the statement is true. Like I said, it's not so much in that proof that you have to know, but the property.